Okay, so this is the lecture track geometry. I'm going to sort of skip to the second example, the derailment at Primrose Hill, Camden West Junction. I'm not going to spend a lot of time on this because at this point in time I want to focus on the issues of track geometry and a couple of key points I want to make. This was a classical track geometry type of derailment. That was because a lot of the track geometry derailments. Oops. Because a lot of the track geometry derailments are track train dynamic derailments, and we said before there are a lot of other components in here. Track geometry problems are present in at least half of the track train dynamic derailments. There's usually some sort of track geometry condition that contributes to this one. So in this particular case, we had a derailment of a freight vehicle, and then we had a container falling off of a flat car. And this is just to show you it's not always the United States, this is the British. I don't pick on French or German reports too much because their reports are always in French and German. And my French and my German are both horrible. Even though German was my PhD language, I cheat because I speak Yiddish, so I know a little bit of German just from my Yiddish. But I prefer to pick on examples from English language. So besides, Israel Railroad in particular has a traditional history associated with British standards. So if it happens in the UK, that's always something of interest. Notice the overhead catenary damage. Some cat poles were knocked down. Okay, so in this particular case, point of derailment was going into this curve here, and without spending a lot of time, the major point that they have here was a question of twist. Now, if you remember, twist is the difference in cross level along a fixed distance. So I have the cross level, left rail minus right rail on one side, on one point, and then left rail minus right rail on a second point, and that distance will vary. So this happens to be 3-meter twist, which means this is the difference in cross level measured 3 feet apart. It's moving, so you're constantly moving down the track. And you can see in this was the twist measurement channel from the geometry carve, and you can see it because it comes close to the standards. So you can see over here, for example, the green represents a track geometry vehicle that was done in November 2012. And so that's the green over here, for example. And the orange over here represents the same location measured again a year later, 2013. So you can see that in a year, in this particular equation, in this particular location, the twist has grown but from about 5 millimeters over here to 20 millimeters over here. And 20 millimeters was already past the 7-day twist limit for network rail. A 7-day twist limit means take action within 7 days of finding it. It's not quite up to the 36-hour limit, which is over here about 25, but the 7-day limit was about 15. And you can see the growth of the geometry defects. We're going to come back to that. Also, what was really interesting here is they also looked at 2-meter, 3-meter, and 14-meter twists. So this distance between the cross-level measurements down here, on this graph, it's 3 meters, but on the next graph, it's 2 and 14 meters. So what's interesting about 14 meters is 14 meters is already getting to be roughly, let's go back here, roughly the bogey spacing on a flat car. So again, we might be in a situation where we're generating dynamic excitation, just like we talked about before. So if you look at the 14-meter twist number now here, you can see that the 14-meter twist number was the order of 45 millimeters, significantly more. See, the 2-meter twist was about 10. The 3-meter twist was around 20. And the 14-meter twist was around 40. And by the way, that's very indicative. The chord length over which you measure a geometry defect will change, will affect the size of the defect, because think of having a long dip. If I measure over 2 meters, I'm going to get one value. If I measure over 10 meters, I'm going to get a different value. And the 10-meter value is going to be more than the 2 or 3-meter value. See, in this particular case, the bogey centers were approximately 14 meters apart. So the 14-meter fist becomes important, because what it does is it resulted in a twisting of the vehicle. The vehicle itself twisted because the front bogey was down one cross level, was going to the right. The back bogey was going to the left, and so you were actually twisting the vehicle, which results in an unloading. And in fact, dynamic modeling of this particular case showed that a reduction, that there was a reduction, that the twist reduced the dynamic force levels and resulted in an unloading. It actually reduced the load on the right-hand wheel of the leading axle relative to the trailing axle, causing that wheel to derail. And if the twist would have been 75% of its value, you might not have had the same behavior. Then also here there was a high coefficient of friction, and I'm going to let you read this on your own because I don't want to spend a lot of time. Basically, the derailment cause was wheel flange climbing over the rail, but in this particular case, we had the cross level, the twist, the change in cross level or twist, which caused the bogey the car body, the wagon body, to twist and unload and cause a low V. So we're back to what we just talked about right before the break. A low V can give you a high L over V and cause you the wheel prime. So having said all that, now let's go take a step back and talk about track geometry defects. Okay, so what are track geometry defects? Track geometry defects are changes, variations from pure straight track in the geometry of the railway system. So it includes gauge, cross level or elevation, cant or super elevation, vertical alignment, which is also called surface, horizontal alignment, which is also called line, curvature, twist, and warp. And sometimes it's the rate of change that can be as important as the defect itself. So let's define a couple of standard ones. Gauge, we've already defined before. Gauge is nothing more than the inside to inside distance between rails. It's usually measured at a point something of the order of 14 or 15 millimeters below the top of railhead. So you have a uniform point that you measure it under, but it's always inside to inside because that's what the wheel flange sees. And of course, we all know standard gauge is 1435 millimeters. Cross level is a variation in height between the left rail and the light rail that's not supposed to be there. So cant is a variation in height between the left rail and the right rail that you want to be there. You design it. You say, I want 100 millimeters of cant, so I put in 100 millimeters of cant. If I have level tangent track and I have no cant, and I go out there and I measure 50 millimeters, then I have 50 millimeters of cross level. Likewise, if I'm supposed to have 100 millimeters of cant and I go out there and I measure 180 millimeters of cant, then I have 80 millimeters of cross level. So it's the variation between the height of the rail, between what's there and what should be there. And in most straight track, it should be flat, zero cross level. In other words, the top of the rail should be even. Alignment is a term. Do I have a picture? Yeah, I'll go back here. So alignment is a variation in both the horizontal and the vertical direction. So let's start with the vertical direction. Vertical alignment also called profile, is variation in the vertical plane. And it's usually defined as a variation in chord length, with the most common chord length being used is the 20-meter chord. So the way you measure vertical alignment in the most simplistic sense is you stretch a 20-meter chord across it, you go to the midpoint, you measure the dip or the variation in that midpoint. Let's say it's 50 millimeters, and that's your vertical alignment deviation, or which is a dip. As I said, we'll talk about how you measure alignment in a couple of different ways, but it's usually defined in terms of a chord. So vertical alignment.
So what is a rail profile?
Say again?
What is a rail profile? What is the difference between profile and a rail profile?
Oh, okay. So a rail profile, which we talked about when we talked about wheel rail contact, is the shape of the top of the railhead.
Okay.
So if I measure the shape of the crop of the railhead, that's the rail profile. The track profile, which is the vertical alignment, is this. Good, I'm glad people are reading my slides. Horizontal alignment is I'm looking down on my track. So here are my sleepers. And I look at the variation laterally. Oops. And both with vertical and lateral alignment, we actually measure each rail independently. So vertical alignment is left rail and right rail, and horizontal alignment is left rail and right rail. So we actually measure alignment separately. Now, obviously this gauge connects the two, the left and the right alignment, and cross level connects the profile. But when you look at your data from your track recording car, it'll say left profile, right profile, left alignment, right alignment. So the horizontal alignment, which in some parts of the world is called line, and I should mention vertical alignment as profile is also sometimes referred to as surface. So if you ever hear the term line and surface, line refers to horizontal alignment, surface refers to profile or vertical alignment. And again, exactly the same way as with the vertical one, we define it in terms of a chord variation. So again, the most common chord used is a 20-meter chord, but it's very, very common to measure horizontal alignments using a 10-meter chord, a 20-meter chord, and even a 30-meter chord, or a 40-meter chord. So 10, 20, and 40 are all used for alignment variations. And in fact, you'll see standards will be written that include a 10-meter chord variation, a 20-meter chord variation, and a 40-meter chord variation. Again, 20 is the baseline. 20 is the sort of the traditional chord length. If nobody says what the chord length is, more than likely it's a 20-meter chord. In North America, in the English world, it will be a 62-foot chord. In the metric world, it will be a 20-meter chord. And again, alignment.
Can I have a question?
Yes.
How you can measure the dip deviation if it's embedded rail, for example?
Well, you're measuring the top of the railhead. So
yes, I know, but you cannot measure the dip because it's concrete there.
You can't measure the dip?
Deepness, yes.
Yes, you can. Yes, you can, because you're measuring it. It's defined at the top of the railhead. So you have an embedded track, okay?
Okay.
So you have a 20-meter cord. You have a physical cord that's 20 meters long, right?
Yes.
You have one person stand at one end and put the cord on the top of the railhead, right? Take another guy, take the second end of the cord, walk out 20 meters until it's stretched, and he puts it down at the top of the railhead. You go in the middle. You go exactly at the middle of the 10-foot point, and you measure the height between the cord and the top of the railhead. That's your dip.
But just because it's not too much, it's in millimeters, this is why I can do it?
It's whatever it's going to be. That's the definition of dip. You're going to probably have less variation in embedded track because it's certainly supported. But if you have any sort of variation in embedded track, you have a problem. But it's always defined from the surface of the railhead. So it doesn't make a difference. So long as the surface of the railhead is exposed, which it better be if you want to run trains, as long as the surface of the railhead is exposed, you can measure your vertical profile.
But how do you measure the hump deviation?
Yeah, I also don't understand. If it's a mountain.
If it's a hump, okay, with a hump, you can't measure with a cord. With a hump, you're going to use one of the more sophisticated systems. Most track recording cars use inertial measurement systems. And with inertial measure systems, you can measure a hump, a dip, anything else. You actually can measure a hump with a cord because as you go along, what's going to happen is so let's say you have your 20-foot cord, you measure it, and then you move down a meter, and you measure it again, and you move down a meter, and you measure again. You're actually going to see that hump created, but you can't easily measure the hump in embedded track. I agree. So, but with an inertial measurement system, you do that, and then what happens with an inertial? Since I'm jumping ahead of myself, but basically, if you have an inertial measurement system, you measure what's out there, right? You just get exactly a map of what's out there on the surface of the rail. But then you define mathematically, since most standards are written in terms of chord length, even today, most standards, most track geometry engines, if you go to Israel Rail Standards, for example, Israel Rail Standards is defined in terms of 10 and 20 meter chords. In fact, I think I have some slides a little later showing you that. So if you have when you take an inertial system, you mathematically draw a point to a point, and then you can pick up a hump very easily. So I can now measure a 20 meter hump very easily if I have an inertial system.
So a hump is like a vertical curve?
Yeah, a hump is a mini vertical curve, except we're not talking about, we're not talking about grades and kilometers. We're talking about, millimeters and meters.
Okay.
So I have 20 millimeters in 20 meters. That's a hump.
Mm-hmm.
But it's still impossible to measure summit in this way when it's embedded. I'm sorry, but I think it's impossible.
Even with an inertial measurement system? Why?
Because it's embedded and it's summit. You cannot measure the depth between 2 points.
if you're, okay, so let's start off with the simplest case. What happened if I have a weld that's not properly ground down? Okay, so I have a piece of embedded track and I put a weld in there and somebody left the weld 10 millimeters high. That actually gives me a slight vertical to the surface, right? Because the surface of my rail is high. It happens to be due to a weld, but I don't care, because whatever causes the surface variation causes the surface variation. I can very easily have surface variation from bad joints or bad welds as I can from failed sleepers or from the support being bad or whatever. I only care that there's a variation in height at the top of my railhead. So you can definitely have a variation in height in the top of your railhead in embedded track. If the pour was not uniform and the tolerances of the pour were bad, we've seen summits or dips and peaks and valleys, so to speak, in slab track and tunnels all the time. Whether it's a hump or a dip, whether it goes down or up, depends where your mean is. Most of the time it's down, but you can have a hump as well. So, did I answer the question? Was that Rena?
Yeah, it was me, but no, I didn't understand, but doesn't matter.
Okay, let's continue this conversation offline. Maybe we'll have an email conversation on this one.
Okay.
Okay, because I don't want to use up all my time right now. Okay, so here's an example of which I showed you once before, but this is a vertical alignment, the profile or surface variations. I mean, this is pretty obvious, isn't it? You can clearly see the profile variations here. I also have a lot of warp and twist and cross level problems in here. So I have everything in this one. I have vertical, I have surface, I have cross level, and I have twist and warp. All three present. You can have all three present. In fact, it's not at all uncommon with track this bad to have all three present. So warp, so let's talk about warp and twist. Okay, so in the British derailment we talked about twist. So twist is defined as the difference in cross level and any 2 points at a fixed difference apart. So remember, they had a 3-meter twist and they had a 14-meter twist. So basically, I go down the track and I say, here's 3 meters and here's 3 meters. And I look at the cross level here, and I look at the cross level here, and I subtract the two, and that's my 3-meter twist. And I go down the track doing that. 14-meter twist, I would have this distance 14 meters. So it would be the distance here and the distance here, and that's the cross level here and the cross level here, that difference over 14 meters. That's twist. What's warp? Warp is the difference in cross level within the specific distance in track, the maximum. So if I was looking at 12-meter warp, for example, which is a number that I've seen used, or if I was looking at 20-meter warp, let's say 20 meters is a commonly used one. I take this point here at 10 meters. Let me erase all these yellow lines. Okay, so I take this point here, and I take this point here, and that's 20 meters. But I would look at every cross level, but I would look at this minus every meter within this 20 meter. And whichever is the absolute worst number, that's my warp. So twist is always that fixed distance apart. So warp is the maximum within that 20 meters distance. So warp is often used to look at dynamic response behavior. Okay, now going back to I think what we were talking about briefly with the discussion with Rena on what happens in embedded track. How do you measure profile, or how do you measure any geometry measurement? The simplest way is by chord offset, right? That's what we were talking about. I have a chord, I have my variation, I look at the variation from the chords, and I just move down the track and doing that. That works. Mathematically, there's an error introduced by a phenomenon called aliasing, which I really don't want to get into right now. You can look it up. You see it a lot in electrical engineering when you look at sine wave type of analyses. So very often, to get around that problem, they use what they call asymmetrical chord offsets, which means I still have my 20-meter chord, but instead of measuring my variation at exactly at the middle of that 20 meters, I go off to the side a little bit, say go around 16 meters or 15 meters, and I measure the offset there. And mathematically, that actually reduces the error. And there's a way of going through that mathematically to show that does that. So that's the way of one way of measuring. The problem is that it's a relative measurement and it's not absolute in space and time. So if I had a 100-meter long dip, and I measured with a 20-meter chord, this would be my number. But I really won't necessarily know that I'm in the middle of this 100-meter dip. I have no way of knowing that because I'm only using a 20-meter chord. So to resolve that, we use a space curve. A space curve is a mathematical formulation that shows you exactly the shape of the surface of your track. And the way you get that is you use accelerometers on board your geometry car, and you double integrate the acceleration, and that gives you basically a displacement. That gives you the space curve. And then if I want to measure a chord off the space curve, I can just come back here and put my 20-meter chord mathematically here and calculate my offset. Why am I bothering? Again, because my standards are written that way. Does everybody understand the difference in concept? It's a very important difference in concept because the space curve is absolute in space. It means I absolutely know where everything is and exactly positioned. I can draw an XY coordinate. I can go through a kilometer, 10 kilometers, and accurately map my surface for kilometers and kilometers. My chord offset is a relative measurement, which only tells me what the variation is over the chord length. In this case, it's 20 meters. But because my standards are written that way, and they're written that way, by the way, because that's how dynamic responses are excited. Dynamic responses are generally excited by the relative variation vertically and horizontally. So that's quite. And so we actually use both in the railway industry. The track recording, most modern track recording cars measure a space curve, and then they mathematically calculate the chord offsets and compare it to the standards. So now let's talk about standards for a moment. If we have time, I'm going to get to track geometry cars, but I really want to talk about standards. In the railway industry, there are 3 commonly used types of standards. There are construction standards, there are maintenance standards, and there are safety standards. So let's pick on Rena for a minute. So let's pick an embedded track. Okay, when you build a track, you specify the standards that you're going to build it to, usually very tight. So you're going to have, your standards are often in terms of 1 or 2 millimeters. You want to build them as tight as absolutely possible. I don't know, Rena, if you remember when they first started coming out with the construction standards for Jerusalem, there was a controversy because they first put out standards that were too tight and the contractors weren't even sure they can control them. So they had to back off on the standards. So construction standards are very, very, very tight standards that you build new track to, but which are, you know, which must be maintained very accurately. Then you run trains. And once you run trains, I don't care if they're light rail vehicles, I don't care if they're heavy rail transit, I don't care if they're passenger vehicles, I don't care if they're freight vehicles, your track degrades. Your track degrades over time. Rail wears, ties fail, get surface degradation, get geometry degradation. And so you introduce the next set of standards, which are maintenance standards. Maintenance standards are standards to which you maintain the track to. In other words, let's say I built the track with a gauge tolerance of 5 millimeters. But my maintenance standards for the gauge, I allow the gauge to go down to 12 millimeters before I have to start worrying about anything. So maintenance standards are the standards to which you have to start taking some action. And you can plan it. Usually with maintenance standards, if I reach the maintenance standards, I have a certain amount of time before I need to where I can do these repairs, I can correct the deviations before it fails, before I have to do something. The third type of standards are safety standards. Safety standards are absolute. Something is unsafe. I either have to take immediate corrective action or I need to slow my trains down. So both maintenance standards and safety standards are speed dependent. Construction standards, not so much, because you're constructing the track to as fine a standard as you can, even though I will tell you, construction standards for yards and sidings are not the same as construction standards for mainline track. So even there you have some variation. But both maintenance and safety standards are speed dependent. Means the faster you go, the tighter, more restrictive the standards are, the smaller the allowable amounts. And safety standards, as I said, are absolute. So because you're speed dependent and you reach your safety standards, you can either take corrective action or you can slow your trains down so that you're within those standards. Okay, so construction standards are most restrictive, very tight, and they're usually for new construction or reconstruction, which is a major effort. Maintenance standards represent acceptable limits of wear or degradation. When your components are worn or degraded to this level, performance is considered degraded. Maintenance should be performed, but you usually have a time window to do that. Safety standards are absolute standards at which it's unsafe to operate. So you either stop operation, which is one option, fix the defect, which is a second operation, or slow down the operation until you allow that. So you really never want to maintain to safety standards. It's a real lousy way of doing business because it means once you do safety standards, you have to take action. Now, construction standards are usually defined by whoever's building the system, whoever the entity is that's defining the construction of the equipment, of the stuff. So in Jerusalem, it was the JTMT that did it. In Tel Aviv, it's NETA that sets construction standards. That's the agency that sets the standards and then contracts it out to contracts to do the work. Maintenance standards are usually set by the operating entity. So Israel Railroads will set its own maintenance standards. Safety standards, depending on where you are in the world, is often defined by government agencies. So in Europe, England, France, Germany, the United States, All those standards are defined by government agencies. In the United States, it's the Federal Railway Administration. In the UK, it's the British Railway Board or the RSSB that defines the standards, as opposed to the railways who define the maintenance standards. So the safety standards, also the safety standards are often subject to independent assessment. So again, in the US and in Europe, there are government safety officers. In the US, the Federal Railway Administrations have special inspectors who have the right to go out on a railway or at any time and inspect. And if they find a defect, or they find something that causes a safety variation, they can shut the railway down until it's corrected. So let's give you an example what this means. So this is an example that I took. Forget where I took it from. It may have been Israel Railways for all I remember. A ballasted mainline tangent track, maximum speed 95 kilometers per hour. Here are my construction standards. Here are my maintenance standards. Here are my safety standards. So my gauge, 0 to 2 millimeters. So 0 means you can never go negative gauge, ever, in construction, and you can go as much as 2 millimeters. Now, let me tell you how tight 2 millimeters is. The rolling standards for rail is 1 millimeter. So the rolling standard for rail is 1 millimeter, and I have construction standards for 2 millimeters. That shows you how tight those standards are. Remember, you have 2 rails. So theoretically, I can be right at my construction standards by just having my rail at the worst part of my rolling standards. My maintenance standards are -5. So minus means tight gauge. The gauge is less than 1435 to plus 25 millimeters, which is significantly more than 2 millimeters, obviously. And my safety standards are -5 to plus 32. So I have between 25 and 32 to do my maintenance before my safety standards kick in. And surface.
Try to say, sorry, Professor, that the safety tolerance is you have to shut off the operation absolutely. You
or
don't have
slow
any mitigation.
Or slow it down. Or slow it down.
It can be followed by speed restriction.
Yes. It depends how large the defect. Give me a couple of slides. What happens is the safety tolerances are speed dependent. So at 200 kilometers an hour, I have one tolerance. At 150 kilometers an hour, I have another tolerance. At 100 kilometers an hour, I have another tolerance. If my defect is more than allowed for at 200 kilometers per hour, but less that's allowed for, say, at 100 kilometers per hour, I can slow my train down to 100 kilometers per hour and still operate.
Okay.
So I can put a speed restriction on depending on the magnitude of the defect.
Of course. But my question is, if between 25 millimeters to 32, we have 7 millimeters, so it can be followed. I don't have to take any immediate action. I can postpone it for a while due to a speed restriction. Is that correct?
Yes.
Okay.
In this particular set of standards. Now, it depends how your standards are written, so we got to be really careful. And I'll talk about that in a minute. But in this particular case, yes, I have between 25 and 32 to take action.
All right. Thank you very much.
But I never, so I don't have to panic at 25.
Mm-hmm.
I have to panic at 32.
Of course, understand.
Okay. So now take a look at the differences in surface, for example. Construction standard 6 millimeters.
Mm-hmm.
Maintenance standards 18 millimeters. Safety standards 55 millimeters.
Well, it's a big gap.
Yes, so I have a lot of room in between here.
Yeah.
Alignment, it's not such a big gap. Alignments is the same 6 millimeters for construction. Maintenance is around 15, but safety is 22. That's because from a safety point of view, alignment is generally more dangerous than surface.
Mhm.
So I'm more worried about alignment. So I have a tighter tolerances for alignment than surface. Most standards have been developed based on track train dynamic behavior. Just to show you the variation, this is the same railroad at 145 miles per hour. So you notice the gauge, remember this was 25 and 32 before? So you notice it's 15 and 25. I have a tighter standard here at higher speed, which is normal happens. Remember this was 55 on the surface, now it's 32. It was 22 on the alignment, now it's 15. So higher speed track has higher restrictions. Like in the United States, and it's this difference around the world, in the United States, we have 9 classes of track. Speed is broken up into 9 categories. Each class has its own set of safety standards. So for passenger equipment, the highest standard of track is 320 kilometers per hour, of which we have no such track in the United States because we don't run that fast. But we do have track in this range because we do run this fast. And we have track in this range and we have track in this range. And so basically 0 to 15 is class 1, 15 to 30 is, 0 to 24 is class 1, 24 to 48 is class 2, 48 to 96 is class 3, etc. That's how the US does it. Here's Israel Railway standards. Now, I don't know if this is the most current standards. This is the last set of standards that I have. So if you tell me it's not the most modern one, I'll apologize in advance. But this, at one point, this used to be Israeli rail standards. So now, first of all, notice we're looking at 4 speed classifications. 0 to 40 kilometers per hour, 40 to 80 kilometers per hour, 80 to 120 kilometers per hour, and 100 to 160 kilometers per hour. So I'm not even sure. Like I said, I'm not sure this is the most current one. But anyway, so basically, in this particular case, what Israel Railways does is, so let's take alignment. And this is alignment over a 10-meter cord, by the way. So at between 120 and 160 kilometers per hour, up to 6 millimeters, I don't have to do anything. I don't have to worry about it. Between 6 and 12, between 6 and 12, I have to do my maintenance. Once I hit 12 millimeters, I need to slow my train down. So if I go out there and if I measure 11 millimeters of alignment, I still can go out and fix it. If I measure 7 millimeters of alignment, I have between 7 and 12 millimeters to fix it. If I measure 11 millimeters of alignment, I have between 11 and 12 millimeters to fix it. If I go out there today and I measure 13 millimeters, oops, I can't fix it anymore. I have to reduce my speed. So the next speed category, the safety threshold is 15 millimeters. 13 is less than 15, so I can slow my train down to between 80 and 120 kilometers per hour and be okay. But what happens if I went out there and I measured 18 millimeters of surface? Something happened in alignment, sorry. I measured 18 millimeters of alignment.
You can go to 40. You can go to 40.
That's exactly right. You have to go between 40 and 80 because you're past the 15 millimeters. You're past this one. So you got to come down here. And if it was 20, I'd have to come down here.
Yeah.
And if it was 26, I'd have to
Inside
stop
of the
my train.
track.
If I had 26 millimeter alignment variation, I have to stop my trains because at this point in time, I don't have any standards that I'm allowed to operate in. And the same principle holds for twist, surface, gauge, super elevation, everything there. Is everybody clear on this? This is really, really important to understand. It's a fundamental principle. So B is my maintenance standards here, and C is my safety standard here. So if I'm below 6, I don't have to worry about anything. If I'm between 6 and 12, I can take my time to fix it so long as I don't let it get past 12. Once it gets past 12, I must do something. Either fix it or slow it down to whatever speed I'm allowed and then maintain it. Likewise with gauge, 8 to 20, and then 25, 30, 30, however I work it. And you notice my standards again are speed dependent. So my allowable standards at low speed, I'm allowed 12 millimeters of alignment variation at low speed without worrying about it, which is double what I'm allowed at high speed.
I have another question regarding this.
Yes.
Now, let's assume that you measured and you're above 6. Okay, let's assume that you're
What am I measuring? Alignment?
alignment. Yes, let's continue with this example.
And I'm above 6, okay?
Don't you have to determine the next measurement? What will be the period between the measurements to see if there is any something evolved?
Okay, now you're talking about the way things should be and the way things really are. In a theoretically perfect world, absolutely. In a theoretically perfect world, you should be able to calculate your rate of degradation, project forward when you're going to reach your maintenance limits, and know when you have to do it in. That's the world that we're actually moving into. The railroad industry is moving into that direction. I run a conference every year that deals with this very, very actively. So it is definitely an area that we're looking to do. But right now, the way most regulations are written, no. The way most regulations are written is you wait until you have a track recording car go there. And when the track recording car, if it measures 13, then you have to take action. Now, most of the standards also tell you how often you have to run your track recording car. So there's an issue. So like, for example, in the United States, for high-speed track, for trains that are running at 200 kilometers per hour, for example, I need to run a recording car every month. I must run a track recording car once a month. If the trains are running at 100 kilometers per hour, I have to run it once or twice a year, depending on how busy the track is, how many MGT of traffic I have. But once or twice a year may be sufficient. But if I'm running at 200 kilometers per hour, I need to run it every month. So I don't have that big a gap. Israel Railways, because it's a small railway, and they have a very expensive and very good track recording car, which they did get from Placer. They run the recording car very frequently on mainline track.
Yeah. Yeah, because it can track about 120 kilometers per hour.
Yeah.
So, yeah.
Amtrak's geometry car goes at 200 kilometers per hour. The SNCF track geometry car goes at 250 kilometers per hour. Yeah, but you can do a lot of measurements, and so you try and for your higher speed track, for your main track, you want to test frequently.
Mm-hmm. Yes, understandable. Thank you.
But the ability to project forward is the wave of the future, and that's what railroads are moving towards. Okay, so I'm going to skip some of this, And okay, just real quickly, visual inspection is still required, but let me just talk about track geometry cars. Okay, I just picked, so there are several different types of track geometry cars, included commercial self-propelled cars. This is a Placer track geometry car, very similar to what Israel Railways owns. These are railroad-built geometry cars, which the railroads built themselves. They make them heavier. There's some advantages for the railroads doing it themselves. These are self-propelled. These have to be pulled by a locomotive. These are the weight of the heaviest freight car or locomotive. These are lighter. So there are a lot of trade-offs in deciding what inspection car you want. It measures all the parameters that we want, but let me just, in the interest of time, I'm just zipping forward with a couple of things. So as I indicated, how does it work? It uses inertial sensors to generate a space curve, and then it uses lasers. So the inertial sensors are usually located on the bogie. So since the bogie can bounce with respect to the rail, it also uses lasers to get the exact distance between the bogie frame, the measurement frame, and the rail. So we have inertial sensors, which are integrated to give you a space curve. And then the lasers are designed to give you the exact location of the rail with respect to the bogie, so you can locate the space curve accurately. So that's a typical track. That's how most modern, this says track geometry cars. I think Israel Railway calls it a track recording car. There's a couple of different terminologies for their use for the track recording cars in the world. These are rail-bound these are all rail-bound, which means they can't get off the rail. There are also high rail truck versions that can go off on highways and go from point to point. They're lighter. As I said, they measure the space curve. Typical outputs. So this is a typical degradation curve. So this is right profile. And you can see this. So let's take this one. This is our biggest peak here, right? So you can see this is June. This is the following December. And this is the following March. So this is in inches, sorry. So this is about 40 millimeters up here. This is about 25 millimeters over here. So you can see how quickly it can degrade, and this is how you follow. So theoretically, and like I said, we're actually doing this, you can project forward this rate. Somebody asked a question? Did I have a question in there? Okay, just some words there. This is cross level. Again, you can see exactly the same behavior over here. You can see the growth in cross level. This is real data, by the way. This was a trouble spot on Amtrak's Northeast Corridor. So you're looking at 200 km/h railroad here. And you're looking at an actual spot on the railroad where you're plotting degradation over time. So you can see, ideally, you want to project forward the rate of degradation. So you can either project forward at specific locations, or you can look at a broader area. So how do we use track geometry information? Sort of my last 5 minutes, I want you to sneak this in here. So track geometry, you look at the first way that everybody uses exceptions. These are exceptions. If I'm past 12 millimeters, I got to do action. If I'm past 6 millimeters, I got to do maintenance. These are exceptions. I have a single standard. I monitor my standards, and so let's say, for example, this was my maintenance, my maintenance point. So all of a sudden, I have to do maintenance. That's at each point-to-point location. Every 0.2, 0.3 millimeters. Most track recording cars measure about every 0.3 meters, roughly. 30 every 300 millimeters, or every foot. The second thing I can do is I can develop what's called a track quality index. So a track quality index is a way of measuring the condition of a longer length of track, let's say 100 meters or 200 meters or 500 meters of track. So I calculate a track quality index. So I go back here and I calculate my standard deviation over 200 meters, and that gives me a track quality index. And then I can look at, and then I can predict the rate of change of my TQI over time and project forward. So the different track quality, there are different track quality indices depending on what's used, but the most common one is standard deviation for alignment and profile, and mean or mean for gauge, or local mean or standard deviation gauge. So this is what this is some British data. We're looking at some data from the British. This is my standard. This is profile or surface. Left surface, right surface. This is my standard deviation. So the larger this number, the worse the track is. And these are different dates that I ran my measurements. So you can see they were taking a measurement roughly once a month. March, April, May, June, July, August, September. So first of all, look over here. Notice it went down. That means somebody did maintenance. There was some maintenance that was performed here. Track never gets better by itself. If you see track getting better by itself, don't believe it. It doesn't happen. Track gets better because you perform maintenance. And then I start looking at my rate of degradation, and you notice it's nonlinear. So right away, a simple linear projection may not work that well. In fact, if I take a simpler linear projection over here, it would tell me I won't have a problem to wait out here, where in fact, reality, I'm coming right up here. If my standard was 4, my standard deviation limit was 4 here, so a linear projection would tell me, you know, I got another 6 months to go, whereas the reality tells me I don't. So this is a projection forward. So this is how standard deviations can be plotted. We can also do the same thing point by point, but the problem is just volume of data analysis. Point by point means you have to do it every 300 millimeters. Whereas this one, I believe this one was a, so let's see, 55.08 to 55.11. So what's that, 0.22? So this is roughly 200 millimeters, roughly. 200 meters, sorry, 200 meters.
What's the distance of measurement?
The difference of calculation is 200 meters.
200 meters?
This is just an analysis for this location. Kilometer 55.088 to kilometer 55.11.
Okay, okay.
220, exactly.
And then I would have another one for 55.11 to 55.33, have another one for 55.3 to 55.5, et cetera, et cetera. So I still have to have these going down the track. You're measuring everywhere. But what I'm doing is I'm plotting across time here. I'm projecting over time. So this is for this 200 meters. So this is the same as this, except I'm doing it now for a much longer distance. I'm calculating this, the standard deviation. So it doesn't give me my worst peak, but it gives me my standard deviation condition. So I have to watch both. I have to watch my peaks, and I have to watch my standard deviation both. And this is just showing it more frequently. So you can see this is in Australia. So you can see the degrade, maintenance, degrade, maintenance, degrade, maintenance, degrade, maintenance. I think I'm going to stop here in the interest of time and give you a second to ask questions, because this is a very important concept. I want to make sure everybody understands. So if anybody has any questions about the use of TQIs or the use of geometry defects, ask that. You can ask now, or of course you can always send me an email. Silence. You guys have been much more quiet this time than you have in the past. Okay. Well, my wife made me promise that I wouldn't go very much longer today because we're technically on vacation. We are on vacation. So I'm going to go back to being on vacation. Again, if you have questions, feel free to email me. I warn you, I may not get back to it till over the weekend, till Sunday. I don't get back till Friday from my vacation, and I'm going to minimize the amount of time I spend working. So again, last chance to ask a few questions now before I say goodbye. Okay, so we will see everybody next week for the last class in this group. Then I will talk a little bit about the exam next week. And the good news is you also get me back in January, so you don't lose me. You don't lose me altogether. You'll go back to some of the other instructors in the meantime, just to get a break. All right, everybody have a good week. It's too early to say Shabbat Shalom. It's only Tuesday, so everybody have a good week, and we'll